Hi everyone, my name is Dr. Bliss, and in this video I'd like to introduce you to hyperbolic trig functions. And these functions sound kind of wild. I mean, we often have not heard of them before we enter Calculus 2, and when we first see them, the name sounds intimidating as well as the notation. But don't let it throw you for a loop. These functions are just another flavor of functions, and just like we study exponential functions and logarithmic functions and trig like sine and cosine, this is just another type of function that sometimes may be useful in your future mathematical careers. So the first thing we want to do when we get a new function in our life is we want to look at the domain, look at the range. How does this function behave? Is it continuous? Let's look at a graph of the function. So we want to get a gentle introduction to how the function works. And then if you're a calculus student, we want to do things like find the derivative and find the integral, things like that. So I've defined sinh, which is the hyperbolic sine function, and cosh, which is the hyperbolic cosine function. And there's also a hyperbolic tangent and a whole bunch of other ones, but I'm just going to focus on these two for now in this video. So the hyperbolic sine function is defined as e to the x minus e to the negative x over 2. So we really know a bit about the hyperbolic sine function because we already have some prior knowledge of what e to the x and e to the negative x does. So for example, let's just gently start with something like evaluating sinh of 0. If somebody walked up to you on the street and said, hey, what's the hyperbolic sine of 0? You would know how to do this already. You would say, well, I know what my definition for sinh is, and so I'm just going to substitute x equals 0. So here we go. We've got e to the 0 minus e to the negative 0. Well, that's kind of silly. I'm just going to write e to the 0 all over 2. And if we keep working this through, e to the 0 is 1, so we have 1 minus 1 over 2. That gives us a final result of 0. And you can do the same thing for the hyperbolic cosine. And you could similarly go through and plug in other values of x and compute other values of sinh of x. Okay, so now let's take a look at the graph of this function. For that, I'm going to hop over to Maple. Okay, over here in Maple, I've opened up a new document, and if I want to plot the hyperbolic sine function, I'm going to tell Maple to plot sinh of x, and I'm interested in negative 10 dot dot to 10. So I'm going to plot this on a viewing window as x goes from negative 10 to 10, and there is our curve. Just looking at the picture of the function, it certainly looks like the domain is all real numbers. I don't see any holes or points of where the function is not defined. So that looks good, and we can certainly go back and verify that the domain is all real numbers. And then in terms of the range, similarly, the output values for y, I'm seeing output values that are scooting up to infinity and down here to negative infinity. So I think that the range also is probably going to be all real numbers. This certainly looks like a continuous function, but let's hop back over to our other screen. So certainly when we come back and we look at what the hyperbolic sine function is, it's this composition of exponential functions. And we know that these exponential functions have a domain of all real numbers. And so that's why the hyperbolic sine function also has a domain which is all real numbers. And so I could just make a note here that the domain is all real numbers. So the domain is negative infinity to infinity. And similarly, the range is negative infinity to infinity. And there's a couple of ways we could reason that. Certainly as x gets really large, you can see that this term would take over in the numerator and this limit would trend towards infinity. And we can make another argument, similarly as x goes to negative infinity, the function would also trend towards negative infinity. And we can do that via limits. Okay, let's take a look at the derivative. So let's find the derivative with respect to x of the hyperbolic sine function. Well, I claim that you already know how to do this, and you already know how to do this because you've already done derivatives of exponential functions in the chain rule back in Calculus 1. So asking for the derivative of sinh of x is the same as asking for the derivative with respect to x of e to the x minus e to the negative x all over 2. Now, using our constant rule, we can pull the 1/2 out in front. And we're left with the derivative of e to the x minus e to the negative x. And now I can use my difference rule for derivatives and just take the derivative of each term. So if I do the derivative of e to the x, that's just e to the x. And then if I do the derivative of e to the negative x, I'll need my chain rule here. So e to the negative x times -1. And we should make a note here that I use chain rule. And in the final step, if we just tidy this up a little bit, I've got 1/2 e to the x plus e to the negative x. And that looks really familiar. That's actually our cosh function. So here what we've shown is that the derivative of sinh is cosh. So again, these hyperbolic trig functions look a little bit nasty when you first encounter them. They're not too bad if you bring it back to first principles and work with everything in terms of exponentials. And then, once you have done a few of these, you'll just know, oh yes, sine, the derivative of sinh is cosh, and things like that. So you're welcome to keep a table next to you if you want to keep some of these identities handy. But the notation looks a bit cumbersome, but they're not too bad once you dig into the hyperbolic trig functions. Again, they're just another flavor of functions. We see them in all sorts of applications,